speaker. It's great to have Ivan Schuller, distinguished professor of physics at UCSD. I've known this character for like 40 years. We sort of wrote some papers together, one of which we didn't publish, but was published by a theorist at the University of Chicago, against our will. Ivan is a Romanian Israeli Chilean who in 1980 got the Outstanding New Citizen of Chicago Award. He is a fellow of the Academy of Sciences of Colombia, Chile, Spain, and Belgium. He's won APS prizes, the Wheatley Award, the Adler Lectureship, and he is a published playwright and an award-winning movie director. He's going to tell us today about physics.
Okay, good. Okay, thank you. So I have a very broad program. As Paul says, I make actually movie. I like to make movies because I feel like we're not doing enough to advertise our wares to the public. I also have lots of friends that claim that they have come to my talks, and so I document my talks every time. And so I know who is in my talks, so you guys cannot pretend. Okay, I'm glad you came. I had you in mind. Okay, so it's a pleasure. I mean, I love to come to New York, of course. At once in my life, I would have given a lot to get a job in New York, which I never got. Now I'm getting older. I'm not sure I really want a job in New York, especially last winter. I would like to thank you. I would like to thank Andy Kent, who was part of this invitation. When I looked at it, I was wondering if I had any pictures of Andy, I couldn't find any picture of him in Cancun. He keeps very secretive. And the only picture I found is some guy going like this. There's some Andy Kent that really lifts weights or something. And I would like to thank Paul also because, as I said, Paul and I know each other since Paul used to be on the bottle. Okay. Huh? Do you know that picture, Paul? Do you know that picture? Okay, so what?
I still have the bottle.
You still have the bottle, the same bottle? Okay, so this year is 35 years since I started working on metallic superlattices, and because of that, the IEEE actually asked me to give a series of lectures, so I promise that I will put up this advertisement for the IEEE, which is the Magnetic Society of IEEE. It's a big society. Well, the IEEE is a bigger society than the Magnetic Society. They also edit a journal, which is the IEEE Magnetics Letters, and so if you guys have any magnetics papers, I'm sure they will be delirious with happiness to publish your work. So when I give colloquia, I usually try to talk about why did I become a physicist, because most people probably have a very different idea of why they became a physicist. Now, the way I became a physicist is because of the reaction that I got to physics when I go around in planes. And so I go around in planes and people that sit next to me ask me, what do you do? And I say, I'm a physicist. And then they say, well, okay, that's very boring. Then they say, that is the subject I never understood in high school or in college. Or they tell you, you must be very intelligent. So you must have come across this, Paul. Let me just dispel you. What they mean by that is actually that you are very boring. Okay, so that's why I want to tell you about... now, why do people think that we are very boring? There is a reason why the people think that we are very boring, because physics, the way we present it, what it is all about, is we usually tell them about springs and about pulleys and about inclined planes, and people really don't give a damn about springs and pulleys and inclined planes. The more sophisticated people think that we are actually deal with bangs. And some people think that we deal with big bangs and small bangs. And in fact, most of us don't do that. And that's what I want to tell you. Okay, so I was sitting at one moment in the lap of Einstein, which is outside the National Academy in Washington. The picture doesn't show very well. I have to go. It was a night. And I was thinking about why did I do physics, and it's related probably to my life, and since this is a colloquium, I feel free to talk about this. So I was thinking, and then so I spent a sabbatical in Paris, and that's both from Paris and from Washington. I was thinking about why did I do physics, and so that's what this talk is really about. So why did I do physics? And the reason that I did physics is because I was very lucky to do my undergraduate work in South America. So I did my undergraduate work in Chile. That's Chile. That wasn't when I did my undergraduate work, actually. This was a little bit later. Okay, it's like last year or something. Maybe I should sit here. I like to look at my own things. And that's a very beautiful country there. You can see the mountains in the south of Chile. And the reason is that I was very lucky because in addition to having beautiful mountains, you have good parties there. So this is in a restaurant in Santiago somewhere. But in Chile, you still can do something that in this country is very difficult to do, is to ask some fundamental questions. And I remember when I was an undergraduate that I was very impressed. I was a math undergraduate. I was studying mathematics, which everybody that starts, very ambitious thinks is going to become the next mathematician. And then I suddenly realized that physics does something that no other area of human knowledge does, which you can ask some fundamental question and you can get something from nothing. And what I mean by that is the following. I remember the first time I encountered the Noether's theorem. So I did not become a physicist because I wanted to know where the edge of the universe is. I did not become a physicist because I wanted to learn where the dark energy is. I became a physicist because I wanted to get something from nothing. And I remember Noether's theorem. I remember this philosophical theorem that the old guys probably all know. How many of you, the young guys, know what Noether's theorem is? Okay, that's good. That's good, the young guys. That's good. Okay, so that's good, because Noether's theorem was very impressive to me, is that you can get conservation laws from philosophy. So if you talk about the symmetries in space, and then you can get something from that. Ginzburg-Landau's second order theory was another one that I encountered the first time that I was doing sort of electrodynamics of continuous media. And because you do a series expansion and you get something, so that's Emmy Noether. That's the best picture I could find of Emmy Noether, unfortunately. And so from symmetry and conservation laws, of course, you can get the conservation of angular momentum. There it is, Landau. Ginzburg theory, you expand things in Taylor series, and from the Taylor series expansion, you can get much of what you want to know about superconductivity and magnetism. So that really impressed me, and so I said, I got to work on this field. I have to work on this field where you can get something from nothing. And so I came to this country and I did something, and I put this up because I want to tell the graduate students that it is a good idea if you do something. And then many years later, I look back at my thesis, and I'm still extremely proud of my thesis. So I published a lot of papers in my life. My thesis work was still something. This is my thesis work, so you can see this is the party that we had after my thesis work. This guy is already retired, was my advisor. This guy is about ready to retire. I will never retire, so, as you see, I had hair in those times also. This is my dissertation, my thesis. And this is what I did for my thesis. I measured what is called the relaxation time of the superconducting order parameter, is how fast the superconducting order parameter relaxes after you disturb it from equilibrium. That is the time dependence of the superconducting order parameter. This was the very first measurement of that, so far as I know. And it has these very interesting properties that it diverges as you come closer and closer to the transition temperature. This is now known. This is the first direct measurement of this. Now it's become again very popular to do what is called pump probe experiments. This was a pump probe experiment on the transition, second order phase transition, and I think it's the first direct measurement of the relaxation of any second order phase transition. This is what is called critical slowing down.
Is this your latest work?
No, this is this is my latest work, exactly right. Very good, thank you. Yes, this is my latest work. My latest work was in 1976. That's why Paul invited me here to tell you about recent things. Okay, so I said, why do I do physics? And this is the reason I do physics. So I could come up with 4 different reasons for. I don't mind, actually, by the way, this kind of interventions. It makes me more be on my toes, and so that's good. So just keep on going, but let me just tell you, crossing swords with me is somewhat dangerous because I am very good at this, okay? Let me just warn you of this, okay? So, and I could come up with 4 different reasons. There are universal behaviors that give you power laws, and I'll show you, if I have time, I'll show you something about each one of these examples. And then you can get into new parameter ranges where you cannot do it otherwise. I'll show you some weird behavior when you can actually separate in one device the charge from the spin of an electron, which sounds totally weird what I'm telling you, and you can ask questions about some big questions, like what is intelligence, for instance. And I'll show you perhaps an example of each one of these if I have time. If not, I'll cut it at any time here, and then we can go to have, I think, some wine or party or cheese.
We'll just take the first three.
Okay. Chicken, don't provoke me with this one. Okay, so now that year when I started doing this lab was my lab was actually declared to be the most productive lab at UCSD, and the reason for that, it was very profound. It was because of this, because Yael Sharoni was born that year, Ivan Miller was born that year, David Morales was born that year, Lin Lin was born the same year. So this was called the most reproductive actually lab that year at UCSD. So then at that moment I decided the collaborations that I will tell you in the beginning were these people. So José de la Venta, who was the main author, was single. Stefan Guenon was single. Siming was single. Gabriel Ramirez was single but got married since then, so I'm not sure that he will be producing anymore. I had a good collaboration in Paris with Alexander Zimmers and also with these three people at the University of Tübingen. And the question, when my students looked at working with me, one of my students put on his thesis, "This, a member of my crew must be tough, ruthless, and never give up, even when things look completely hopeless. What makes you think you qualify?" He says, "I worked with Ivan Schuller." Okay, so the work that I will tell you, it was that kind of a work. Okay, so what I'll tell you is about the metal insulator transition in vanadium oxide, VO2, to reduce this to practice. VO2 is only two elements, is sort of the most simple thing that you can think of, and this already is a very rather spectacular curve if you look at this. The electrical resistivity of this material as a function of temperature in a very narrow temperature range changes by several orders of magnitude, sometimes by as much as 7 orders of magnitude, the different phases of vanadium and oxygen. Sometimes V2O3 can change by 7 orders of magnitude, VO2 changes by 4. This is actually it's a rather spectacular experiment which is not actually still well understood. It's an old known thing. It was discovered by Morin in 1959, and it's not well understood. Now, why would anybody by something that was discovered in 1959 would be working today on this? Now, I'll tell you why. So here it is a sample of vanadium oxide, which is that black thing there, and these are some electrodes. And if you look at these electrodes, the distance between these two electrodes here is very narrow. The distance between those electrodes is bigger, but they are all in the nanoscale. They are all very small. And if we measure that resistance, the resistance, of course, this is a 200 nanometers. The sample, you can see there is the resistance changes by 1, 2, 3 orders of magnitude. It's just like I described it to you in the bulk. But if you look a little bit in detail at this measurement, you find that there is something weird there. See that thing doesn't look smooth, that curve somehow. It's not smooth. And then you start wondering, well, don't I know how to measure a resistance, which has been my life quest, is to measure resistances, and so how the hell can't I measure a resistance properly? So when you look in detail at that measurement, you find out that in fact that's not an experimental error. That in fact the way the resistance changes, it doesn't change continuously. It changes in steps, and then there is a smooth change there, and there is another step. And so if you cycle this back and forth, you see lots of steps, and the thing is not reproducible at all. So you wonder, what the hell can I do with a measurement like this that is not reproducible? I can never do two measurements that are exactly the same. Okay, in fact, if I look at this and I expand in one scale there, it is scale invariant. There is always a big step, and there is lots of small little steps. And then you take that thing and you expand it again. There is a big step, there is lots of small little steps. And you keep on expanding this scale, you find always the same. So there's big steps, small little, lots of little steps. Okay? Now, you think, well, what can I do with this? I can't do anything with it. Well, in fact, you can do something with it. And what you can do with it is you can look at the number of steps, number of jumps, as a function of jump size, let's say in ohms. And if you plot that in a log-log curve, then you see there is something quite fundamental in that. It's a universal curve. And it's a log-log. In a log-log plot, this is a straight line, which means that the dependence in the statistics of those steps is some kind of a power law. In fact, the power law goes with some exponent alpha. Okay? And at the end of the story, the reason that is because of this. So as Chaikin just came back from Aspen, is because of skiing. because it happens that transition does not occur. What the hell is going on? It does not occur, okay, as in a smooth fashion, but it occurs like this. Okay, I don't know what this is, not in the full screen, but that's okay. You can see there. Okay, so it occurs. It's very interesting way. So there is the skier. You see there is some small, I hate these snowboarders actually because they destroy the mountain. But, they throw some small things there. And then as it keeps on going down the mountain, as you will see it in a second there, okay, suddenly there is like a big avalanche that he launches. Okay? And then, okay, so then eventually the guy survived. Okay. So, yes.
That's an effect of a size effect?
No, there is no length scale in the problem, actually.
No, but this scaling behavior
yes.
occurs with the 200 nanometers.
No, it occurs in all of them. What happens is there is a length scale, actually, if you plot. Okay, so that's a very good question. In fact, we investigated that. Every time a physicist tells you it's a good question because he knows the answer. Okay, so now I know the answer to that question. As a function of size, if you make the sizes bigger and bigger, then the steps become smaller and smaller, and eventually it looks like a smooth curve. So that's why it was not seen before. It has to do with so in this type of samples, it occurs at, let's say, 6 micron size, electrode separation size. Begins to be detected.
And the hysteresis
yes.
was also.
The hysteresis is still no. The hysteresis no. So the hysteresis in both going and coming, there is this step effects.
That hysteresis is also involved.
Yes. Okay. All right. So then basically what happens is that this transition is triggered, and then it develops, and then there is many small avalanches, and there is one big one. And so what happens is that basically the way this transition occurs is that there are little pieces there, like Pierre is asking here, there are little pieces that have this metal insulator transition, then they have the metal insulator transition, and then the physics of it is in that exponent, because that exponent tells you how much coupling there is from one piece of the material to another, and then the exponent changes depending on how this is coupled. And so you can simulate this actually quite well. Okay? So this shows you that there is some universality to this physics. In fact, when you start investigating where there are power laws, then you start discovering there's power laws all over the place. So, for instance, earthquake magnitude. Since I lived in Chile many years of my life, then this is very dear to my heart. There is number of earthquakes as a function of magnitude is a power law. The power law is 1.2 in the case of the earthquakes. That has to do with the way the strains in these earthquakes is coupled. For instance, this is the number of nodes in the internet, okay, as a function of connectivity. That is also a power law. The power law there, I've forgotten what it is 2.1. That tells you how much interconnectivity it is. This is another plot that my students did, the number of papers as a function of number of citations by Ivan Schuller. Okay, the power law there is 1.7. I don't know what's the meaning of that, but it tells you something about the connectivity of Ivan Schuller to the rest of the world. Okay, and there is many other examples. Barkhausen noise, plasma burst. You see, this is very attractive to a physicist because you can see that this thing appears all over the place, and so this tells you that many of this behavior is some sort of an avalanche behavior. And I can tell you a whole lecture about this, how this occurs and why does it occur, and so on and so forth. Okay, but I just wanted to show you that there is some kind of a universal behavior, and that's what. Okay, so that's my first part of my talk, the universal behavior. Okay, so now new parameter ranges. So now what I told you is that this occurs only, as Pierre was asking, this occurs only when things get very small. Now what do I mean by things getting very small? What I mean by things getting very small is, the chemist's view of the world is something like this, a positive charge and a negative charge is circling around it. That's called a molecule for the high energy physicist. This is the solid state physicist viewpoint. It's some kind of a solid with a battery to it, and somewhere in between there is a length scale which characterizes what is called nanoscience. So I guess that's what people call nanoscience. And the reason that I'm showing that is because that is full of surprises. And so, well, the first surprise is that there is a famous French theorist. His name is François-Marie Arouet. Pierre, you cannot say. You probably know who this is, right? No. So that's François. No, everybody has a nanovoltmeter in their lab, and so and he said this in a book of his. I have his book here actually. This is the book that you can buy it if you go to Paris. You can buy it in the Pantheon. It's right there. he wrote a book called Micromegas, which was the first story, as far as I'm concerned, about nanoscience. Was by this famous theorist, and he compared the size of a man to the size of the Earth. That's what it says there, and he says that the ratio of the two of them is like 1 to 91 million something. And then he said, if you compare that to the size of a ball, then an animal that lives on that ball of a size of about 1 meter would be of the order of 10 nanometers. So that's the first nanobio. The name of that guy, see, that's nanobio, which people call. And this is the guy, and his name is Voltaire. Okay, he's buried in the Pantheon, and he wrote this book, this story. It's a very interesting story called Micromegas. You can download it. Actually, I was in sabbatical in Belgium, and this guy, André Magnan, was the president of the Voltaire Society, told me about this. Okay, so I started working on this in 1980 because I decided, okay, I will work on something that nobody else works, and I had this idea, which was not that brilliant an idea, is to make metallic superlattices. Everybody at the time was working on semiconductor superlattices, saying that's it, that's where all the applications will come from. Actually, metallic superlattices eventually led to much more applications than semiconductor superlattices. In fact, it led to this Nobel Prize in 2007 to Grünberg and Fert, and now everybody uses it in the read heads. For me, it was a pleasure that this Nobel Prize was awarded to Grünberg and Fert because I got an honorable mention there. So if you look at the discovery of the giant magnetoresistance, the Nobel Committee, it says there that several publications prior to the work of Fert and Grünberg, that was in 1987, so it says prior to the work of there, that's Ivan Schuller, you see there? I don't know if Paul Chekin is not mentioned here, but... This was after I left UCLA. Okay, well, it is prior. You see, it was in 1979, and the rest of the work was in 1987. So that was quite nice to see that. Okay, and this led to a lot of applications. So if people only care about application, people always start these talks by talking about this application, like hard disk drive, memRAMs, sensors. And all these are based on a 4-layer device. It's based on a giant magnetoresistance tri-layer, which is a ferromagnet, some kind of an inert material, and another ferromagnet, and then next to it an anti-ferromagnet. So the giant magnetoresistance, I will only tell you about science. I couldn't care less about applications. And I tell people, even my sons, that the reason I don't care about applications because I haven't done anything useful in my life, and I'm not going to start at this age to start doing something useful. So the hell with the applications, I don't care. But it's interesting. So why is it interesting? So let me tell you, there's a lot of interesting things. So for instance, giant magnetoresistance is this effect that comes from these tri-layers. That there is a huge change in the resistance of the material with the magnetic field when you couple these three layers together. And of course, that's what gave Fert and Grünberg the Nobel Prize. There's another interesting thing is that you never worry about is that if you pass an electron through a small little device, and if the device is small enough, the electron carries a momentum, and the electron flips, the momentum gets transferred to the material. That nobody ever worries about this, but eventually people started worrying about it, and now Andy Kent is making a living out of this, and I hear that he's going to make $1 million or something. Is that true? Much more than $1 million, okay. Out of basically this fundamental question that people were asking about the change of how does the momentum gets transferred to this kind of devices. So these are currents going through these small pillars. They are called spin torque devices. And then I myself spent a lot of time worrying about this interface here between the antiferromagnet and the ferromagnet. That is called an exchange bias situation. That will not make me any money, unfortunately, although a pretty good living. And that is called exchange bias. Okay. So what I want to say is the following: is that this is also from my thesis, by the way. So this is very recent work, as you can see. Woodstock says, this is rain, it helps things to grow, it fills up the lakes and oceans so the fish can swim around it and gives us all something to drink. Woodstock doesn't care what it is as long as he understands it. And I saw this cartoon in 1970 and I kept it forever, and then I asked Schultz for permission and he let me reproduce it in my thesis. So this is in the first page of my thesis. So what I want to emphasize here is that basic research is very important, and that's what leads to transformative technology. And I want to make a big advertisement for that because there is this dichotomy of people in physics First saying that, well, you have to work on the Higgs boson because that's the most fundamental thing, or you have to work on some application that makes spin torque, oscillators or something. And I would say, no, you have to do basic research, and that will lead to transformative technology, and that's important, and there is no way to know where. Okay, so I showed you something about new parameter ranges about GMR. Now I want to show you something about weird behavior. So this is the work that was done with a bunch of people, in collaboration with a bunch of those people that I showed you in the beginning. So this is the real Cheshire cat. Those of you guys that are not American, the Cheshire cat comes from Alice in Wonderland, and there was this cat that had a big smile. Sorry?
American?
Well, okay, sorry. Yes, you're right. Yeah, it's English, but okay. No, I'm just saying that it's not the people that are not American have never heard of this. No, Anglophobes. Okay, yes, okay. So, and the interesting thing about this cat is that he leaves his smile behind. Okay, and so the smile stays behind, and so this is something that actually it's very good for a public lecture because it sort of allows me to say things that actually people get very fascinated, and then there is a lot of debate about this, which is the following. So it's a device that looks like this. So here it is a normal material, and I put two ferromagnetic electrodes there on top of it. Okay? The way I put those two ferromagnetic electrodes there, that I can flip the moment of this ferromagnetic electrode compared to that one. And then what I do is I will put a current in this loop here. Okay, so the current will flow in this loop. Now, mind you, I teach electricity and magnetism as we speak now. In fact, yesterday I had to skip it to take a plane to come here. So I teach exactly this. So I put a current here, and then I measure the voltage there. And this is an insane experiment. If you think about it, and I teach my students in 2B that this is an insane experiment. If I put a current here, and there is no current there, there should be no voltage there. Okay? And here it is the device, so you can actually make these devices. So this is a device made in my lab. There it is the two ferromagnetic electrodes. There it is the normal metal electrode. They are quite close together. Again, all these businesses, you have to know how to use the technology to make these things. But you can make this, and you can make it pretty much with any normal material like copper or aluminum, and any magnetic material like permalloy. This is an alloy of iron and nickel or something, and cobalt or something, and you can do that. And you can put a current there, and you measure the voltage between this electrode and that electrode. And then a miracle happens. So here it is the voltage that I'm telling you, the voltage which you shouldn't get any voltage as a function of magnetic field. Now, why am I showing it to you as a function of magnetic field? Because the way to flip the magnetic moment of one electrode to the other, you arrange the electrodes in such a way that when you apply a small magnetic field, let's say less than 800 Gauss, then this moment stays put, but this one can flip. So by flipping a magnetic field, you can flip this moment up and down. Okay? So this is not a magnetic field-induced effect. It's just an effect due to the fact that the moments flip. Okay? And you find this very interesting effect. There it is. The voltage, this is the so-called non-local voltage, divided by the current that flows in the primary electrode, it comes along like this. There's a big voltage drop there. And then if you come along the other way, it does the other way, the opposite. Okay? And then there is even a memory effect, and this can be... Oh, sorry, I don't know why this thing is switching on its own. And so this basically has a memory effect, and this can be actually, some people advocate that this could be useful for devices, and it could be used in memory devices because it consumes less power, because there is the amount of current that you circulate there is very small. Okay, and so therefore this consumes less power in the switching.
So the green line?
Sorry?
What's the green line?
The green line is depending on how you do. So if you go all the way here, and then you sometimes let's see, I've forgotten exactly how it is. That if you come here and then you come back, the device stays at the same level. Then it switches, and then if you don't go all the way to the end, but you can come back on the same level. So it keeps memory of where it switched. Okay? Yeah.
You apply the magnetic field to both of them.
Yes, you apply the magnetic.
Only one of them responds.
Flips, exactly. Only one of them responds, and the reason for that is because you arrange the anisotropy of them in such a way that only one of them can respond. Okay? So that's what the trickery is of screwing around in the lab and doing something. Okay? So So this is very interesting because this is sort of a non-local behavior. And in fact, when you give a public lecture, you tell, look, what I'm telling you is the following: is you have a ball, the ball is spinning like this, I move the ball this way, but the spinning of it moves that way. And I can measure the spinning of it moving that way. That's a kind of conceptually to people find it very interesting that you can do that. Okay, you can separate the spinning from the object itself. Of course, the background here plays a role, but you don't have to tell them everything. Okay. Well, I mean, when some more intelligent people, actually, you wouldn't believe it. I've given public lectures where I talked only about this, and then people ask me, "How can that be? That's impossible." And I got into a debate in purpose, and then when I told them there is the background, then they kind of said, "Oh yeah, that makes sense now." Okay, but it's a very interesting effect actually. It's this non-local spin bar effect. Okay, and so that's a kind of a weird behavior. And now I will tell you about big question: what is intelligence? Okay, so now this started me actually many years ago. I started thinking about this. So about 4 or 5 years ago, when I started thinking about this more seriously, I looked at what is the biggest computer that there is in the world. So for $200 million at that time, Los Alamos had this computer which had the 12,000 processor and huge memories and this storage. And I looked at this computer and said to myself, this costs $200 million. For $30,000, I can do something that works much better than that. And I'm virtually sure that most of you can do that also. And here it is an example of that. His name is Jonathan Schuller, okay? So this 31 years ago I made this. It cost me about $30,000, okay? And the reason I'm bringing this up is because Jonathan could do things. Actually, Jonathan just got married last year, very close by here in the plaza there. Actually, his family in which he married, they're both professors here at NYU, so I was here at his wedding. Anyway, so Jonathan also became a physicist, by the way, in between these 31 years. Now, when he was a baby, I was always looking at him, and he used to touch his mobile and look at his hand, and then touch his mobile and look at his hand. I started wondering, what the hell is this kid doing? What's going on through his mind? And so I came to this idea, which may be right or may be wrong, but never mind, that's how research works, is that somehow sensors, that the connection between sensing and the brain is very important. And so therefore, I wanted to see if I can do something. So that's what he taught me, okay? So are there any unifying principles? And so I thought to myself, okay, well, in my mind, the unifying principle, at least some idea, is that you cannot have developed intelligence without having a connection to the outside world. And so I said, okay, so this is what is called biological inspired. I look at that kid, which is a biological object, and I'll see what I can learn from him. And so my wife really likes this when I show this, because I show my son, and then I say, okay, so what does he have? He has a central processor sitting there, okay? And then he has some sensors, and then he has some local processors, which allow him to figure out if it's hot or cold. Then he communicates to the central processor, and then he has some feedback, which allows him to reduce. So that's my son, Jonathan. Okay, my wife really hates it, so because I put it in proposals, more like this. Okay, so there it is, my son Jonathan reduced to his essence. Okay, and so I said, okay, well, so this sounds very intelligent, but who the hell cares? I mean, nobody's going to be able to fund this, and nobody's going to. So I said, okay, well, will that the word nanoscience that kind of pulls in some more dollars to do something like this? And so then I decided, okay, how can I convince somebody? So you make it wireless, this connection, instead of making it wired. And then how can I convince somebody? Well, actually, in the New York Times of 2003, there was this article that actually claimed the same as I'm claiming, that communication with the outside world is important. But never mind that. The question is, how can you reduce this to practice? Because besides just talking about this, who the hell cares? Can you do something practical that somebody is going to be willing to spend? And so, brings me to the hard problem in this business, which is funding. Okay? So this was the work that eventually led me to look at organic thin films. Okay? And so what we eventually ended up developing was the sensors that are both very sensitive and very selective. And this is based on this material. Okay, so this is the reduction to practice to all this nonsense bullshit about intelligence. Okay? But it started like that. What can I help you? So this is a material which is very interesting to me as a physicist, because This is a flat molecule. This phthalocyanin is a flat molecule that has a metal ion in the middle. It's called a metallophthalocyanin, and pretty much you can put any metal ion in the middle. You can put copper, iron, nickel, cobalt. You can even put 2 hydrogens there in the middle. Okay? And you can stack them up, and I know how to stack them up. This is actually turns out to be a very useful molecule because, see, it's blue. It's actually blue. It does not colorize. It's blue like that, and you use it in your blue jeans, actually. They colorize some clothing with this, with copper phthalocyanin. Okay? So it's a useful molecule. I mean, it's used for a long time. Now, I know how to grow it, and there it is how we grow it. There it is, we put it on what is called a molecular beam epitaxy system. That's where now this thing becomes expensive, and I know how to grow this phthalocyanin on top of this substrate. And here it is, the device, finally. So it turns out that metallophthalocyanin is very useful to detect resistively the binding of volatile organic molecules, like benzene, like DMMP, which is dimethyl, I don't know what, some weird thing, which is a simulant for nerve gas. If you remember, there was a Japanese guy that tried to kill a bunch of people in the metro. This can detect DMMP. So this is a detector for instance, for methanol. Here it is the response of the detector. Here it is the input that we put into it, and then it is the response of this detector, and then there is the details that come. How big is this response? Why is there the drift? How do you get rid of the drift? These kind of things become very practical issues. But at the end, it's very sensitive. This is in parts per billion, actually, that you can detect this thing. And that's actually a device that eventually led to two or three companies to actually pursue this, and they're pursuing these as real sensors. And it led to this. Now, why is this not working? This is a mystery. Can you guys hear it or no? No? Wait. Okay, now it may be too loud. So while actually there are three companies or two companies that are trying to develop this, and it's very good for detecting peroxides. Actually, it turns out that peroxide is an important ingredient in this explosive devices that terrorists use. Okay, so it's very good for that, because depending on whether the central ion is cobalt or it is copper, it either acts as a donor or as an acceptor, the peroxide, to this thing. And so it gives you a very distinct signature. Okay, but you have to have like a nose. You have to have more than one signature. Anyway, the reason I put this up is not because I particularly think that this is somehow the ultimate in technology, but it's because I think that this illustrates how disruptive technology can arise totally unexpectedly from revolutionary basic science. That basically I started wondering about, my son touching mobiles and things like this, and then it led to looking at sensors. Yeah?
I'm sorry, that's like quite a jump, right? I mean, yes, intelligence needs to sense the outside world. So you sense some chemicals, but by that standpoint, we need not vision to understand the world. Yeah. So if someone's using lasers, they're studying intelligence. I mean,
well, okay, so if that leads you to some, it's okay. I mean, all I'm saying to you is that never mind. I mean, you're trying to analyze my psychology, my way of thinking. I mean, the fact that I connected those two things, it's kind of not very important. What is important is that I started worrying about basic questions. Then I started worrying about basic questions about sensors in organic molecules, and based on that, which nobody would have led anywhere, it led to some actually very well defined application. So whether my psychology and my way of thinking was the correct one or not, I'm not.
He's not trying to explain intelligence. He's trying to explain where inspiration comes from.
Exactly. That's what I'm trying to say. I'm not trying to say that I explained to you intelligence, not at all. I'm trying to tell you is that my inspiration came from some kind of irrelevant thing that I was thinking about it, and then I connected it to some practical thing because I needed funding. That's what the bottom line is. Okay, so let me just say a few words about targeted research. So this is targeted research that was in 2010. Scientists from the Rand Corporation have created this model to illustrate how a home computer could look like in the year 2004. This was 60 years ago. However, the needed technology will not be economically feasible for the average home. Also, the scientists readily admit that the computer will require not yet invented technology to actually work, but 50 years from now, remember this was written 60 years ago, scientific progress is expected to solve these problems with teletype interface. That's this thing here, and the Fortran language, which was invented by the Egyptians. The computer will be easy to use. Okay, so I would be working on the third. If I would be, just following the research on this, that's what I would be doing for my home computer. Okay, and this guy would be sitting on your lap.
What does that wheel do?
I don't know.
We're not there yet.
No, this is too sophisticated. Okay, so there is another thing that actually got me last year to think about things, and I'm going to finish just on time, which is some other inspiration. Now, again, this is not that I'm trying to necessarily solve the ultimate problem that I start with. And that's how basic research is. You start with some problem, and you start doing research, and then you end up somewhere else. And that's the nature of this beast. So if you think about the brain, so this is what got me last year in sabbatical. I did a TV interview to Walter Kohn, actually. You can look it up in the web. And I asked Walter, hey, Walter was in my department, so I feel free to call him Walter. I asked him, wait, Walter, how did you come up with this density functional theory, which Pierre was actually a big man in that thing? I said to him, and Walter said, you can see it in that TV, he said to him, Ivan, I was in Paris. And you know how Paris is. Paris leads to big thoughts. So for years I've been circling around in Paris, trying to see. And last year I lucked out and I was in sabbatical in Paris. And there was a guy that gave a set of lectures about the brain, about neurons, and things like this. And I went to this lecture and I suddenly started thinking about this, and maybe I'll do something about this. And you'll see how this is connected to the beginning of my talk. So, if you think about the speed of a neuron, the size, the reliability, and the dimensions, and the energy consumption you find, and the temperature range in which it works, you find that the brain has about a speed of about 1 microsecond, has a size of somewhere between 1 micron and 10 microns. It's about 80% reliable. I could still give this talk with 80% of my brain. You can shoot 20% of it, and still I can give this talk. It's three-dimensional. It consumes only about 10 watts of energy. And it works in a very narrow temperature range. You raise. It is about 1 microsecond. the pulses that go around in the brain.
So you're saying action potential is the ratio of microsecond?
No, I think that's much narrower, but it takes 1 microsecond between pulses. And it responds like that. You switch it. Okay, so how fast do you switch it? It doesn't matter. See the exact numbers of this. Milliseconds is even worse. Okay, good. So you're making my point even better. Fine. Milliseconds. Good. Thank you. That makes my point even better, in fact, because what I want to compare it to the technology. So we can, in a computer, we have a transistor. The transistor works on nanoseconds. We can make transistors somewhere. I can make easily 20 nanometer transistors in my lab, but we can make it even smaller. The reliability is actually much more fantastic than the brain. It is two-dimensional so far, but you can increase that. And the energy consumption is several orders of magnitude worse. And it works in a very broad temperature range. Nevertheless, the brain can do things that technology cannot do. Okay? And so that actually has led to what is called new schemes of computing, which are not von Neumann type of schemes. And there's a lot of people that are worrying about that, and I think this is very interesting kind of ideas of MEM computing or neuromorphic computing, what are called neuromorphic computing or bio-inspired computing. This is not something that you want to switch over to do neurosciences. This is just to implement in solid-state devices that have these properties. Okay, and there is a whole lot of people that are actually advocating this, and I think that actually vanadium oxide, believe it or not, actually Hewlett-Packard is pursuing vanadium oxide as a neuromorphic element for computing because it switches and it has multi-states and it can actually do things that... Okay, so what did I tell you? I told you in this talk that you can make nanohybrids, and these give you new materials which we can manipulate nature. We can make some kind of intelligent nano devices which extends our reach, so we can do targeted action. And then we can biologically inspired devices, maybe can understand ourselves. The importance is that there's a confluence of physics, chemistry, materials, scientists, and biology. And of course, the results that will come out of these are unpredictable. That's what I think is the final summary. The future, as Niels Bohr said, is the hardest thing to predict. Okay? And so what are the grand challenges? So I'll put up a bunch of grand challenges here for the students. Because I was talking to the students, and they don't want to hear all these details about vanadium oxide and, who the hell cares. They want to know grand challenges. So here it is, some grand challenges. Look at some bio-inspired, like look at the brain and see if you can make an artificial brain that works like the brain, that is not von Neumann-like. There is a grand challenge for you. Look at, okay, this is something that most solid-state physicists don't want to accept, is that in all devices that we produce today, in all materials that we produce today, disorder plays an important role. And therefore, that you have to take into account. And instead of fighting disorder, you may want to embrace disorder. Okay? Very short time scale behavior is not understood, and there is a lot of big machines actually that are being built, the LCLS, femtosecond machines, where you can actually look at chemical reaction occurring in real times. That's a sort of a... And maybe one can build artificial solids by this business of stacking things up and lithography and all kind of things. There is a question, there it is, a question for you guys, a big question. What is life? I have no idea what that question even means, but that's a big question. And I think that interaction with the external world, like I've been discussing here, that was a sort of an important, at least, inspiration to me. So, in summary, this is what I want to leave for the students, that the most important summary is something which is, I actually learned this from my father, which said, when I was a very small boy, he said to me, you know what more important is about, instead of doing what you like, is to, above all, like what you do. Okay, and you see, there's my father, and that's where I was. I already had this attitude. This was in Romania, actually, 60-some years ago. The other thing is you want to enjoy the process, and this was said by a Spanish poet, his name is Machado, and he said, that is Machado, he said, caminante no hay camino, se hace camino al andar, which means that you have to enjoy the process. If you don't enjoy the process of doing this thing, and all you want is the ultimate result, then that's not the right thing. I mean, it's more important to enjoy the process, how you develop these things and all this kind of stuff. So this is why I did physics. This is actually from Paris. I was checking. I'll leave it to you to guess where this is. Okay? But anyway, so that's why I became a physicist. And so I'll leave you with these grand challenges, and I'll be happy to answer questions. And I'm right on time. Thank you. Holy cow.
Can you beat a dog yet with your sniffer?
Can we beat a dog? Okay, so let me put it this way. Yes, I don't think a dog can as easily detect peroxide. Try to have a dog detect peroxide for you, which is the important thing. So these sniffers, what they are good for is they're both sensitive and selective. That's the key. Sensitivity is not that big a deal. As I tell people, I'll kill you if you tell say this, but I always say my wife is very sensitive, but she's not very selective, okay? So this is selective also, this sensor. So yes, we can beat a dog as far as peroxide is concerned. I don't think we can beat a dog on everything. But that's a good question.
The dog is the standard. Right?
What?
The dog is the standard.
Yeah, but the dogs, they don't use them for peroxide. They use them more for things like marijuana and things like that, which nowadays is not very important to detect, as you pretty soon will not be important at all. Okay. And I'm not sure why.
Dogs are not selective, although to some extent they make the dog smell something,
yes.
and then the dog will look. So
yes.
that's a form of selectivity.
Right.
But you're saying that's not hard to beat, whereas the sensitivity.
Right. The sensitivity is hard to beat. So the problem with the dog, I can tell you, the one problem with the dog. In fact, I had a personal experience with that. I was flying from somewhere into the U.S. and suddenly discovered I had an apple in my bag and said, shit, I'm going to eat this apple. So I started eating the apple while I was walking through, and then they pulled me aside and they chewed me out because basically the guy said that the dog basically got overwhelmed by this apple. I mean, basically the apple just confuses the dog completely. So the fact that I ate an apple in the same huge room, this was, I've forgotten where, in Los Angeles or somewhere, it completely confused the dog. So the selectivity of the dog went to hell with that, me eating an apple in the room. Well, so what's with you graduate students? You guys were so interactive when I was there, and now suddenly you guys, why are you guys so shy? Okay, come on. It was funny because they were very interactive while we were there, and then they said they become very shy in the seminar room.
I'm kind of curious how you're bio-inspired. What do you think are really promising research directions?
Well, I think
oxide that's a material with metal insulator transition.
I think that materials with metal insulator transitions are very interesting because there are certain properties that they have that are very similar to this kind of neuromorph needs. For instance, they are multi-state. So you can have the multi-state. Now, they have the problem that everybody says, well, they are very narrow temperature range because they only work at the hysteresis region. But, of course, that's why I put that up for the brain. The brain also works on the hysteresis region. You hit me up too much, that's it, it's finished. Okay, so they are multi-state, they consume very little energy, they are non-volatile. So it has a lot of properties that are very similar. I'm telling you that Hewlett-Packard actually has a whole project on this. Now, whether that will lead anywhere or not, who knows? But Hewlett-Packard does have has a project on vanadium oxide specifically. As far as I'm concerned, vanadium oxide is very interesting. I'll tell you why, for instance. Just let me give you an example of disorder. You take VO2, which has this metal insulator transition at 340 degrees. You take V2O3, which has the same metal insulator transition at 165 degrees. VO2 and VO3 are basically the same. VO3 is just VO 1.5. I mean, it's nothing different, okay? It turns out you damage it. You put radiation damage on VO2, and the VO2 is extremely stable. You put slight amount of damage on the VO3, the metal insulator transition goes away. So the disorder, the effect of disorder on these subtle different two materials that are phenomenologically the same, the disorder on one is much more radically affects one than the other. Nobody understands that. Why is that? Now that's some very recent work. It's actually not published that we have done very recently. There's a bunch of theories that are arguing there among themselves. Okay, so there's interesting scientific questions. What is the effect of disorder on these things? And let me tell you this. You will hear many solid-state physics talks, probably in this room, where people will try to tell you, you have to push things becoming more and more perfect. I'm saying the opposite. I'm saying don't try to not worry about, because everything is going to be always imperfect, as far as I'm concerned. And therefore, it's much more important to understand what the effect of disorder is on these things. And if any device that you build is very critically dependent on thing being perfect is probably not very useful. Okay? Yeah?
So can I ask a bio-inspired question about your sniffer?
Okay.
Which is, I mean, the reason your sniffer is better than a dog is because the dog doesn't have a peroxide receptor.
Yeah.
Right? And so you've made something that's very specific to one chemical.
Right.
It's like a pheromone detector or something.
Yes.
But in general, the way olfactory systems work is you have a bunch of different receptors. They're all
Yes.
somewhat broadly tuned.
Right.
And the organism detects the odor by which the set of receptors it's over.
Right.
So do you have any progress making devices that somehow could be broad?
Yeah, so this is exactly, thank you very much for that question, because this is exactly what this is. It turns out that the peroxide detector works not on the fact that cobalt phthalocyanine is sensitive to peroxide. It works on the fact that cobalt phthalocyanine acts as an acceptor, and copper phthalocyanine acts as a donor, and therefore the voltage that you get is opposite in sign. And so therefore developing something like that is not necessarily the most sensitive detector for peroxide, but that it's like it has a discriminating, so the Fermi level is somewhere in between there. That's precisely how it works. And so this project was not to develop one sensor. The project was to put multiple sensors on just like a nose, exactly. So that was exactly the idea. So that's where the inspiration came from. So it's exactly bio-inspired. Put many sensors around. In fact, when I looked at Jonathan's fingers, it has many, many sensors there. So I thought, you want to put many sensors on the chip, and many different kind of sensors. In the finger is temperature and I don't know what, acid and this kind of thing. There it is going to be peroxide and methanol. So that's exactly the bio-inspired. Oh.
I saw during the lecture that you were very much interested in how disorder works in solid-state fluids and how it can affect different states, I guess. So what I was wondering was, because as you said, most people try to achieve perfection within a solid, right? Zero entropy, something like that. But your lecture implied that disorder is not only advantageous; it should be pursued in a specific manner. So
right.
I wanted to know how far into that research are you, and how far the world has gone into that this grand challenge.
Okay, good. So the question of disorder is a very interesting one. Somebody once said, I forgot who it was, but Frenkel, maybe one of these Russian physicists, that said what makes silicon interesting is not silicon itself, but the defect. It's like people. It's the defects that makes it interesting, okay? Now, I can give you an example where I believe that disorder plays a major role. The rest of the world doesn't, but never mind. I think it's disorder. You take lanthanum aluminate. Lanthanum aluminate is a material which is a complete insulator. Okay, it's like glass. You can look through it. And you take strontium titanate. Strontium titanate is also an insulator. You take those two insulators, complete insulators, you put them together, and presumably at the interface, if you have them perfect and you have them in a certain order, which of course nobody has proof of that, but never mind that, then it becomes conducting. It becomes metallic. So you take an insulator at the interface. Just at the interface, yes. It becomes metallic. That's the claim. Well, I've done some experiments myself, and I claim that it has to do with disorder. That in fact, that's all the effect of disorder at the interface. That the interface is disordered, and because it's disordered, it's conducting. Okay? So I'm telling you, there's many things that people like to believe that this comes out of the perfection of the material, and then they argue to death that these materials are perfect in order to be able to explain it to you. I believe that it comes from disorder, and then you can use that disorder to build, for instance. So you can build the disordered interface between lanthanum aluminate, the disordered interface of strontium titanate. The oxygen efficient strontium titanate turns out to be superconducting. And I believe that the superconductivity of this interface between lanthanum aluminate and strontium titanate originates from the oxygen defects. It does not originate from the perfection of the material. You see, so that's another way of looking at the thing.
So you think you wouldn't have a 2D electron mass at the interface?
Well, if you look at the measurement, just very recently I heard a talk by this guy, Changbom Eom, who's an oxide guy. I don't know if you know the guy. He claims that he measured the width of that interface, that the width of that interface is about 2 nanometers, which is about 20 angstroms, so it actually extends quite a while, and it's very disordered. It doesn't look very thin, and that has to do with, I believe that has to do with It doesn't have to do anything with the perfection. It has to do with the disorder. Okay?
It does need to be mentioned that the Pope of condensed matter physics,
yes,
or at least one of the popes of condensed matter physics, got a Nobel Prize and on his understanding of disorder,
right,
and has made many other contributions to physics that are focused on disorder.
He means Phil Anderson, I presume. Yes, definitely.
Yeah.
Right.
I mean, that's certainly it is a lesson that's maybe hard to learn, but we've heard it from him and.
Right. The problem is, the problem here is that today in this oxide business, for instance, everybody kind of claims that they can, if they put in strontium titanium, they put the titanium oxide on the surface is different than if you put the strontium oxide on the surface, and they believe that they can actually do that. And then when you push them, okay, go show me evidence for this, the whole thing collapses. And it turns out the width of the thing is 20 nanometers, which is several unit cells, right? And so, the whole thing collapses. So that's what I'm saying to you. And that's because there is this mindset that you want to claim that you do better than God. Okay? And then, therefore, I say, no, embrace the defects. And there is nothing wrong with the fact that the defects are there, and try to use them.
Certainly biology doesn't avoid defects.
Yeah, exactly. Biology.
You can't do LDA very well now with a superset.
Exactly. That's the problem. You got it. Exactly. You cannot do LDA, and so therefore everybody wants to do. But try to do LDA for and explain vanadium oxide with LDA, and then I'll listen to you more. Okay? Because nobody knows how to explain even the metal insulator transition with the simple electronic structural calculations. I mean, yeah?
Yeah, something else I wondering if you could say a little bit more about. So we were kind of zooming into this fractal with this insulator inductor thing, and then we watched this video of the snowboard get crushed by an avalanche, and I started talking about earthquakes, and all this had to do with this power law behavior, and you said you had a whole other lecture that you could give about that, and I was wondering if you could just kind of sum up what exactly is it that is common between these things?
Okay.
It's not just this plot.
Okay, I tell you what it is common, is the following, is that the way the metal insulator, imagine a square lattice of resistor, a resistor network which is a square lattice, to be very precise. And imagine that each one of those elements can switch between a metal and an insulator. And now, imagine that if one is switched, the next neighbor to it has more probability of switching than if one is not, if it's surrounded by 4 insulating, okay? No, that can happen for a variety of reasons, but never mind it. Okay? Then you can see how this occurs. One switches, then another one switches, then suddenly one resistor finds itself in a much more favorable state because it has 2 nearest neighbors, and then this thing occurs as an avalanche. First, you switch one, you switch the other, you have the small resistive changes, and then suddenly you launch a whole avalanche. And so that's the big step. Okay? And that's what gives rise to power laws.
What you actually need is disorder for that.
Yeah, you need disorder for that, yes.
Otherwise, it'll just...
Yeah. Right, you need disorder, exactly. Right. Yeah.
Some lovely statistics about
Right.
the size of
Well, the problem, I can tell you what the problem is with that statistics. As soon as you get into this and you ask questions about sizes and things, there is a problem, because since this is self-similar, then you kind of have this feeling that there is no length scale in the problem. And so therefore it's not clear what the length scale is in the problem. Is that answer your question or not? Okay, so this issue of length scales is an interesting question, but I don't know, I don't have a good answer for it.
Okay, I think we should thank Ivan again.